So polarity and bonding are closely related. Polarity really comes from why bonding occurs. So that's the best place to start. Bonding occurs so that atoms can be in the lowest energy state possible. So the molecules are able to save energy as opposed to when the elements are in their atomic state. So the lowest energy state for an atom is reached when an atom has a filled outer shell. For most things, it's a full octet, with the exception of hydrogen, helium, lithium, beryllium, and boron, which can exist with 2 electrons in their outermost shell and have full stability. And that's just because their first energy level can only hold 2 electrons. So depending upon what atom bonds with, they can gain, lose, or share electrons. So this is going back to the bonding thing. So ionic bonds have to do with if a bond with an atom has a much lower electronegativity, what's going to happen is they're going to transfer an electron. So the electron's going to go from the metal to the non-metal. So if they bond with an atom with a much higher electronegativity, they will again transfer an electron to form an ionic bond. So in an ionic bond, you're forming ions, which are charges, so what's going to happen is the non-metal will steal an electron from a metal to form an ionic bond. So ionic bonds, we are transferring the electron. So all the different types of bonds, we're doing different things with the electrons. So the other type of bond we have is a covalent bond. With a covalent bond, this forms if they have roughly the same electronegativity. So instead of they're not strong enough to fully take or transfer an electron, they're going to share the electrons. So if the difference, so this is for a small difference in electronegativity. All of bonding is really based on the electronegativity. You can actually calculate the electronegativity difference to determine the type of bond that will form. Covalent bonds we can actually break apart into 2 groups. We can have ones that the electrons are shared equally and when the electrons are shared unequally. So if their electrons are shared evenly, they're going to form a non-polar bond. So if you think of something that you share, maybe a candy bar with a friend, if you break that candy bar exactly in half, you're sharing it in a non-polar manner. So you're sharing those electrons exactly equally. For a polar bond, it's going to be an uneven sharing. So same idea with the candy bar, maybe someone gets 1/3 and the other person gets 2/3. So that's when you have a slightly larger electronegativity difference that you have that uneven sharing of electrons. Where are the electrons going to go if they're shared unequally? Well, they're going to go towards the item that is a higher electronegativity, and this gives partial charges. We've talked about partial charges a bit, but the way that we identify a partial charge is with a lowercase delta. You kind of draw it like an 8 that is incomplete. So this represents a partial charge. So this would be a partial negative charge, for example. You can also have a partial positive charge. So if you think of the hydroxide group we have here, the oxygen is more electronegative than the hydrogen, so it's going to end up with a partial negative charge. Another way you can think about this is you can think of how many lone pairs of electrons they have. So oxygen has 2 lone pairs of electrons. So generally the thing with more lone pairs of electrons is going to be the more electronegative item. So with this relationship between the hydrogen and the oxygen, so the more pairs on the atom the electrons are going to spend more time on the atom that has more lone pairs because they tend to be more electronegative. This arrow is representing the movement of the electrons. We're not going to really focus on how you draw the arrows and what the impact is on them, but just keep in mind you can kind of track this and it does have other implications. We're kind of taking a basic look at it. Okay. Oops, that's too far. So this sharing of electrons unevenly is referred to as a dipole. So a dipole is when you have part of the molecule that has a positive charge and another part that has a negative charge. So rather than an ionic bond where you have one thing that is completely positive and one thing that is completely negative, so if you had sodium, it would be positive, and chlorine, it would be negative. We now have regions. So we have a positively charged region and a negatively charged region, such as in water. So if there's two chlorine atoms, each sharing one of their electrons so that they have 8. The easiest way to look at this is by using the Lewis structure. The Lewis structure helps to indicate what's happening with your sharing of your electrons. Chlorine is a diatomic, so it's always existing in pairs. So one of the things that you can look at with this, with the polarity of it, is how are the electrons being shared. So if it's sharing with its identical twin, such as with chlorine and chlorine, then it's going to be sharing completely equally. If you think of a tug of war between two identical twins, assuming they have approximately the same strength, it's going to be a pretty equal match. Now, if you had, the quarterback of the football team versus someone else that's maybe not so strong, well, against me, let's just do against me. Chances are the quarterback's going to win because they have a lot more strength than I do. So how do we go about determining the polarity of a molecule? We draw the Lewis structure, we determine the symmetry, and we look at the lone pairs. I usually look at the lone pairs first, because if there are lone pairs on the central atom, it's going to be polar for us. So if you think about this, there's two shapes. We have trigonal pyramid and bent. These two shapes are always going to be polar, 100% of the time. With symmetry, we're more looking at what are the types of atoms that there are. So are there the same atoms or are there different ones? So if we take a look here, I have an example of a symmetrical molecule here and an asymmetrical or non-symmetrical. Oxygen in water here has two lone pairs. So this first one is completely symmetrical. We have 4 of the same things bonded with the carbon, so it's going to have a non-polar notation. Water, right now, this is asymmetrical, but the lone pairs also there indicate that it is polar. Let me give you an example of another non-symmetrical molecule. So let's say we had carbon with 3 fluorines and 1 hydrogen. This would be an example of an asymmetrical atom that would be polar, because the hydrogen is going to share the electrons differently with the carbon than the fluorine and the carbon. There's this table you can use of a series of questions to help you determine if it's polar or nonpolar. And when we talk about polar and nonpolar, it's really not two groups. There's kind of things in the middle that are sort of polar or sort of nonpolar. We call it slightly, and that's more complex. We're not going to really get into that as much, but just keep in mind there is that differentiation. So this brings us to the idea of intramolecular forces and inter. So intramolecular forces are forces between the atoms that are chemically combined. So what do I mean by chemically combined? They're either transferring the electrons or sharing the electrons. So this is an ionic or covalent bond. We're not really going to take a look at metallic bonds because those are a bit unique. We're primarily focused on ionic and covalent. So a water molecule. So this right here, this bond, is an intramolecular force. It's within the water molecule, as is this bond. Intermolecular forces are forces between atoms and molecules that are not chemically combined. Not chemically, I guess, would make more sense. So look, I have an example here of 2 water molecules. We just went through talking about partial charges, how oxygen has a partial negative and hydrogen has a partial positive charge. So what's going to happen, and this is what we're going to talk about in just a moment, the hydrogen of one molecule is going to be attracted, dotted lines are not working so well here, to the other oxygen. So I just have two molecules here. Think of how many molecules you would have in a glass of water. There's going to be a lot of these interactions kind of making a network between all of the water atoms. And this is what we refer to as hydrogen bonding, which we'll discuss a bit later. Hydrogen bonding is when you have one molecule attracted to another. Oh, this should be partially negative. I wrote it as positive for some reason. So the hydrogens are both partially positive, the oxygens are both partially negative. Sorry about that. So as I said before, we look at the electronegativity. Here's a good chart of the electronegativity. The only thing I don't like about this is krypton and xenon. They have a pretty high electronegativity, which I don't think helps us, so we just kind of ignore those for our purposes. If you go on to take a more advanced chemistry course, they can discuss that. But you'll notice here that nitrogen, oxygen, and fluorine are the most electronegative atoms on the periodic table. I like to refer to them as NOF, N-O and F. Because they're the most electronegative, it has an implication that we're going to see in just a few moments. So in your notes, you have this chart. You just need to fill in the definition part. I'd recommend writing that in, maybe pausing the video and filling that in. But we're going to go through and talk about this. So we have the first here, which is called London Dispersion Force. It may also be referred to as van der Waals. They're the same thing. They're just two different names. What this is it's an attraction between two instantaneous dipoles. So what is an instantaneous dipole? It's a dipole that occurs, another way of saying this is it's temporary. So it happens for a moment. So for a moment we have two partial charges from an asymmetrical electron distribution. It happens for a moment. It is not permanent. This occurs in every single atom. So polar, nonpolar, this happens in everything. You can kind of think of this as happening by chance. You happen to have all of your too many electrons on one side of your molecule than the other. So this is a little diagram to show you what's happening. This is a very, very weak interaction. This does increase in strength as the mass increases because you have more electrons. So if you had a helium versus a xenon, the xenon's going to have a much higher or much stronger London dispersion force than helium because there's more electrons. The more electrons you have, the more likely it is for something to be an electron to be misplaced. So we refer to this as LDF a lot, which stands for London Dispersion Forces. So that's the weakest. So a note here, this is the only intermolecular force that can occur for a nonpolar substance. So anytime you have any sort of chemical substance, it's always going to have London dispersion forces. It's just we tend to focus on the strongest. So the strongest for a nonpolar molecule really is London dispersion force. The next one we have is a dipole-dipole force. So this is attraction between two permanent dipoles. So this occurs in polar molecules. So as I said before, polarity is kind of a scale. So this is for polar molecules where we have an unequal electron distribution. So here I have HCl. The H is going to have a partial positive charge and the Cl has a partial negative charge. So what happens is one HCl with another HCl is going to be attracted here. It's not a very strong attraction, but it's a little bit stronger than it's significantly stronger than the London dispersion forces. So we refer to this as medium strength. We're going to give you some numbers to associate with this in a few, but for right now we're just going to talk about this as being medium strength. So this is stronger when the molecules are closer together. So if you think about a charge, if you have them closer, they're going to be stronger attracted. That makes sense. So the next one has an awful name. Hydrogen bonding is not a bond. It is not a chemical bond. I can't tell you that enough. I will tell you right now, on your test, you're going to have a question. Which of the following is not a chemical bond? Ionic, covalent, metallic, or hydrogen? Can't tell you how many people don't pick hydrogen. Hydrogen is not a chemical bond. All a hydrogen bond is it's an attraction. It's really an awful name. So a hydrogen bond is an attraction between an nitrogen and a hydrogen, oxygen and hydrogen, or fluorine. So that's where that NO and F, those are the three most electronegative. If it has an NO or F with a hydrogen, then it's a hydrogen bond. So these are very, very, very polar bonds. They're extremely polar. So therefore, you can think of a hydrogen bond as an extra strong dipole-dipole force. So water is an example of something that has hydrogen bonding. So the hydrogen of one water molecule is going to be attracted to the oxygen of another. So even though this is the strongest intermolecular force, it's still not that strong. And we're going to compare this to chemical bonds in just a moment. Okay, so how do we determine the intermolecular forces? An ionic, when we have something that's ionic, that's a bond. It's really not an intermolecular force because you have the full attraction of both. So ionic, that's a bond, not an intermolecular force. So if we have a polar molecule, there's two things that you could have as the strongest intermolecular force. So you could have dipole-dipole, or you could have hydrogen bonding. The only time that you will have hydrogen bonding for us is if you have a hydrogen bonded with a fluorine, oxygen, or nitrogen, which is that NOF that I was referring to before. So if it is a hydrogen bonded to one of those three and it's polar, it's a hydrogen bond. If it is hydrogen bonded to a carbon, or hydrogen bonded to something else, it is not a hydrogen bond. And remember, that's an awful name. It's really not a bond. So polar molecules have a permanent dipole. They still can have LDF. Everything can have a London dispersion force. Nonpolar molecules can only have London dispersion force. That's the only possibility they have for these intermolecular forces that we're talking about. They can only have the London dispersion force. So they often have temporary induced dipole from random movement of electrons. The bigger the atom is, or the molecule is, the more likely that it's going to have this intermolecular force because there's more electrons. So it is something that is there and does occur.